Okay, hello, I'm Dr. Rowan Kenway. I'm the Head of Research Computing here at ARC at UCL. That means I'm in charge of the team that looks after all of the HPC systems that we provide to our users and we provide nationally. ARC is a new organisation, it's a little over a year old, that's spun out of Central IT. It's basically the crumbling bones of what used to be called Research IT Services. And so we've spun out into our own department with our own remit, which means not just running HPC systems, but also doing research and collaborating with people as well. So about a year and a bit ago, before we were ARC, I gave a talk, which is basically this talk, which is how to use one of our HPC systems that we provide called Myriad as an example. But the information in this talk also applies to all the other systems we provide. So, what we're going to go over in this talk. So first of all, I'm going to talk about how you access an HPC system. So you have a laptop on your desktop. How do you log in? How do you run commands? Then I'm going to talk about how you manage your workloads on an HPC system through a thing called the batch scheduler. And finally, I'm going to give you some tips on how you can arrange your jobs so that they run efficiently. So first of all, how do you get access to our HPC systems? Well, our systems are free to all researchers at UCL. This is because we are funded from the central pot of money that's created when your grants are top sliced. And if you're at UCL, you can apply for an account by going to this URL here. If you go to our website where our documentation is held, as you can see on the screen there, if you look on the left-hand side, you'll see there's a link here for account services. And if you scroll down, you see a user account application form. This will ask you to sign in with single sign-on, and when you do that, you will it will autofill. Once you've signed in, it will autofill in a bunch of your details, so you don't have to type them in manually. Okay. Once you've got your account, you get access via a protocol called SSH, and I'll go over what that is in a minute. You have to be within the UCL network, so that either means you have to be physically at UCL, you could be logged in via the VPN, or you could be using desktop at UCL remotely. Those things put you inside the network. You have access to the login nodes only interactively by default, and you have access to the compute nodes via a batch scheduler. And we use one called Grid Engine. So let's go back to the beginning, right? You want to access an HPC system. So in the good old days of the 1970s, when everything was better, your department or your university would generally have a large computer, which slightly perversely was called a mini computer, something like a PDP that ran Unix. This was shared between many, many users, and you would interact with it by having a dumb terminal or like a very early home computer connected through a serial line or a phone line. And when you connected, you get a command with a command shell. You would type your commands, press enter, you get your responses back, and so on. Because home computers were very much an early thing at this point, right? We were very early in the development of having home computers. Generally, you have a dumb terminal. A dumb terminal doesn't store any files on it locally, so there's not really any file transfer protocols, but there are some things you can use called Z-modem, which allows you to bring files back to your computer if you have an early home computer. If we step forward to the 1990s, which is about the time where I started getting heavily into using computers, we'd moved on a bit. So in the meantime, ARPA had funded this thing called the internet, and that meant that most of the machines we wanted to talk to were connected to that, as was your home computer, admittedly through a phone line. So you generally connected through your home computer or a computer on your desk at work, through the internet or through the local area network at your university, to a mini computer running Unix, much as you did before, or possibly even to a custom supercomputer, right? And a custom supercomputer was a very fast, very purpose-built machine. These were very much sort of I think one of my previous bosses used to describe them as the F1 cars of the computing world. They're fragile and fast, right? The serial terminal connection was abstracted over a TCP/IP protocol, usually Telnet or RSH. These were very early. This was before people generally realized that encryption was absolutely essential for pretty much everything on the internet, so nothing was encrypted. There was a file transfer protocol called FTP, which is actually, that's what FTP stands for. Again, not encrypted. There was some very early adoption of SSH, which is kind of the first encrypted protocol for logging into machines remotely. Nowadays, almost everyone's home computer is a laptop, because apparently desktops are over. You still connect over the internet, but you're really connecting to a machine that is no longer a purpose-built supercomputer. What it really is a large collection of standard web servers that have been repurposed, plugged into a very fast interconnect switch and a large file system, and that you can run parallel jobs on, right? The serial terminal is now always abstracted over to SSH. No one lets you log in through Telnet or FTP or RSH. Those are all considered really insecure because your password travels in plain text. Never mind your data, right? If you're doing anything with any kind of private data, you absolutely cannot use those protocols. But SSH not only provides that serial terminal connection, but it also provides a suite of file transfer tools, and that's because it's very good at tunneling other protocols, and I'll talk about that in a minute. So there are tools like SCP and SFTP which let you transfer files to and from the machine that you're working on. So what is Secure Shell? So Secure Shell provides a virtual serial terminal to a host over the internet securely and encrypted. All home computers that are relatively modern come with a version of Secure Shell installed. It used to be that on Windows you had to install a different application called Putty because it didn't come with it, but a couple of years ago Microsoft's really embraced sort of collaborating with Linux. And you'll see some of that with like the Windows subsystem for Linux stuff, but also they now bundle SSH in their installation from about halfway through the life of Windows 10 onwards. So what happens is you open a terminal window, or in Windows a command prompt, you type SSH, then your user ID, the @ symbol, and then the host name of the machine, right? It also provides tools for doing file transfer. So it provides SFTP, which is again the same syntax, but when you do that, that's interactive and looks a lot like a file transfer client from the 1970s. It's still command line, but it's fairly friendly and interactive. You can also use SCP, which kind of looks like the copy command on Unix. So you do SCP, the user @ machine : file to the user @ machine : file, right? SSH has a very complicated plug-in mechanism for doing authentication, but the most common pair are having a username and password and using SSH keys, both of which we support here at UCL. Another nice thing, in order to prevent a situation, this is kind of grew up before TLS became really popular, but in order to prevent a situation where you connect to a remote machine and someone else is sitting in between that machine and you and just listening to your calls, right? So it's transferring data, it's sitting in the middle and pretending to be the other machine. The first time you connect to a machine, SSH stores a thing called the host key for that machine, which is a unique key which identifies that machine. And if that ever changes, it stops you from logging in and gives you a big scary warning. It also allows you to do tunneling of other traffic, and that's actually how the file transfer parts work, right? It also lets you do things like if you want to port forward something for like a Jupyter notebook, that works. And most commonly this is used if you're on Unix or Linux on your desktop. You can run a thing called the X server, and then you can run graphical applications on the remote machine but have them display on your desktop. SSH keys, these are really helpful, and I've got them set up so when I do my demos later, you'll see I don't have to type in a password at all. They let you generate a two-part key pair, a thing called a key pair, and there's a private part and a public part. And the private part you should keep private, and you should treat that like it's your password. You must use a passphrase when you create it. So when you create the key, it'll ask if you want a passphrase. Do not create an empty one, because that'll mean that that key is not encrypted, and anyone who finds the file can then log in as you anywhere, right? If you encrypt it with a passphrase, then they need to know the passphrase to decrypt it. You have the option of using the DSA protocol on some older machines. You should not use that, it's very old and is now insecure. And what you do is you generate your key with the passphrase, you put the public key in this file on the remote machine called ~/.ssh/authorized_keys. Note the American spelling, this always catches me out. And what that means is that you no longer need to log in with your password, right? And you might go, well, I put in a passphrase, so now don't I just have to use that? Well, again, that problem is solved. There are very nice tools built into Linux and Mac, and I believe Windows as well, where the first time after you log in the morning, you have to type your passphrase, but then it's kind of cached forever after until you log out again, right? So I'm going to do a demo now where I'm going to log into Myriad, which is our high throughput cluster. Let me bring up that terminal. I have already put in my passphrase previously because I've been working all day, so it wouldn't ask me for a password. But here you see, as you see, I have a terminal, I type SSH, my user ID is UCCAOKE. Those of you who are familiar with the way UCL allocates IDs will realize this is a chemistry ID. That's because when I did my PhD, which was the first interaction I had with UCL, I was a chemistry student. The @ symbol and then the hostname for Myriad, which is myriad.rc.ucl.ac.uk, and I press return. And that's it, I'm logged in, right? I can run commands, very traditional command line interface. If you've used Linux at all before, or the command line on your Mac, you'll be very familiar with it. And it's okay. Back to the presentation. So, batch scheduler. So why do we have a batch scheduler? So resources on any shared system are limited, right? This slide is a little bit old. It says Myriad has only 5,000 plus cores. It's actually more like 15,000. So we've expanded by effectively 3 times the size since these slides were created. But each workload that a user runs can be hundreds of thousands of individual tasks, right? And we have many hundreds of users across all the departments in UCL who all want a fair chunk of the resource. And so the way we mediate that is we have a tool called the batch scheduler, which is a program which you submit your job, your piece of work to. So you wrap your piece of work up in a thing called a shell script, which is a text file with just a list of commands that you would type in at the terminal, and some resource requests like how much memory, how many cores you want, where you want it, what directory you want it to run in, and so on. It puts all those jobs into a queue, and then the scheduler is constantly adjusting the priority of those jobs so that they run when resources are available. So the upshot of this is you can submit your work on a Tuesday, log out, it will run sometime, possibly overnight, possibly a day or two later, come back and get the output of your job. So that's the workflow, right? You write your job script, you submit it to the queue, you go away and have a coffee, attend some lectures maybe. Depending on how busy the machine, this could be days. But when your job is ready, when the resources for your job are ready, that will run on those resources, and you'll get some files with the outputs and any errors that happened put in the directory utility. There are 4 basic commands, of which 3 you'll need on a daily basis. qsub is the command which submits your job script. qrsh is less useful for this workflow, but what it does is it lets you submit a job that becomes an interactive terminal. So it's like SSHing into the compute node, but you have to wait for a node to become available, and obviously that could be days. So the usefulness of that is limited. qdel lets you delete a job that you've submitted previously, and qstat lets you see the status of your jobs in the queue. Right, and now I've got a little demo of where I'm going to submit a job. So, all of your jobs are effectively shell scripts, right? A shell script is a list of the commands that you would run at the terminal. And when you run the job, it acts as if it's just logged in as you for the first time. So a good example of a command you can run is the date command, which prints the current date and time. There's another one, which is the hostname command, which prints the current hostname. I'm currently logged into login 13, which is one of the login nodes in rotation at Myriad. So let's write a job script that actually does that, right? That runs those 2 commands on the remote compute node that it runs on, and we'll submit it to the queue. Right. In sort of Blue Peter style, I've prepared one earlier. So if I look at example. So the start of every shell script has to have a thing called the shebang. This tells it which shell to use. So the shell is the program you interact with when you type commands. So we tell it to use bash, and we tell it to be a login shell with -l. That's very important because of the way that a job is run, right? It logs in as you for the first time, and for your environment to be set up, it needs to be a login shell. We then put in some special comments so a comment normally starts with a hash, but there are special comments like this one, the hash bang or shebang, which tell it what shell to run with. And these special comments, which start with $, tell SunGrid Engine, which is our scheduler, what the resource requests you have are. So here I've put L, which says resource request, hard runtime limit, H_RT, slightly annoying name, but okay, is 10 minutes. I want it to be given 2 gigabytes of RAM. I want it to be given 10 gigabytes of temp storage on the disk. This is seriously excessive because all we're going to do is going to run date and hostname. And I tell it to run in, and I've made an error here, see? In the current working directory, which is -cwd, and we want to run date and host new. So we save that. So we've got our shell script. So we want to submit it to the queue. We do that with QSub. And when we do that, we get back a message here saying your job and then a number has been submitted. And that number is your job's unique ID. So when you want to interrogate the queue about the job, or if you want to delete the job, that's the ID number. We can see that the job is in the queue by typing qstat. You see I've got one job in the queue. When you type qstat, it only shows your job. So the machine is actually extremely busy. There's hundreds of other people running jobs, but by default, it only shows your jobs. And if we wanted to delete that job, we can delete it with qdel. Right. I'm not going to do that right now because we want to run it. We can see that it's got a job ID, it's got a number here. This is the priority. It's currently set to 0 because the scheduler hasn't looped around and adjusted the priority on this job yet. Got the name of the job, got my user ID, we've got the state, so QW means it's in the queue waiting state, it's waiting to run. And later on that'll turn to an R for run, and then when it's run, it will vanish from the queue. This is a slightly annoying field in that it is either the submit time if the job's not run yet, or the time the job started if the job has started. And slots is the number of cores it's requested. So we didn't request any cores, so the default is 1, right? You can request multiple cores, and then you'll have a bigger number in there. We have a lot of HPC systems available at UCL. The two that are predominantly targeted at UCL users are a machine called Kathleen, which is for HPC, and that's for large MPI jobs that take more than one compute node to run on. So if you've got hundreds or thousands of cores in your job. We also have a high throughput machine, which is Myriad, which is the one I've just demoed. And that's targeted at workloads where you have to do thousands of similar analyses, right? So a good example is, I don't know, you've got a couple of thousand samples, you've got an analysis program, you write one shell script, submit it as a job, it runs all those analyses and all the different data, you come back in a week or whatever and you get your output, right? It also has GPUs in it, which I will talk about in a different talk. And it also has support for very large memory. So sometimes you have workloads that require like a terabyte of RAM. They can be run on Myriad. We run a lot of different services. This slide is still in date, I believe. So we have Kathleen, as I described, which is for these parallel workloads, Myriad, which is the high throughput machine. We run a machine called Aristotle for interactive Linux teaching. And that's predominantly because various departments need a system that they can let their students run Linux commands on, and most of the desktop systems at UCL are Windows. We also run two national services. We run a machine called Young, which is the UK-wide Tier 2 Materials Molecular Modeling Hub. And we run Michael, which is a similar machine to that, which is for the Faraday Institution for Batteries Research. We, as part of our design principles, the software stack on all these machines is the same. So if you log into Myriad, and you log into Kathleen, and you log into Young, the environment will be very similar. They all use Grid Engine, they all have the same applications installed. The only difference is that on Young and Michael, because they're national services, there's a charging regime on there. If, like me, you think of things better in pictures, here is how I try to explain the difference between HPC and high throughput computing, right? If you're doing an HPC job, you're running on thousands of cores, what you do is you generally have one input file, right? You run your program on tens or hundreds of nodes and they communicate with each other while this program is running, and then you get some output data. The point is these subtasks all have to run at the same time because they have to communicate, right? There's dependency internally in that communication. High throughput computing, on the other hand, you have lots of input data, you have lots of independent tasks, and it doesn't really matter what order they run in. If task 7 runs before task 6, it doesn't affect the output, right? These are completely independent workloads. Myriad is UCL's high throughput / data intensive service. It has almost 15,000 cores, 64 GPUs across 3 generations, 18 high memory nodes. It has a petabyte of loss to storage. It has both free and paid access mechanisms, so it's free at the point of use, but you can pay to have nodes added to the system for your use. Kathleen is UCL's primary HPC service. It's from HPE. It uses a network called Omnipath to do the MPI communication. It's got 7,680 Intel Xeon cores, 40 cores per node, and a petabyte of luster. As I said before, we have a common software stack deployed across all our resources. I think this is again out of date a little bit. It's more like 850 user applications now. And that includes a whole range of tools, from development tools like MATLAB and Python to applications like BLAST and NAMD. And there's a lot of programming languages on there because one of my hobbies is programming languages, and I tend to add them to the system when I'm working on them, experimenting with them. But generally, if there's something that's not on there that you want, you can put a ticket to our support desk and they will add that to the list of packages to install. The idea is that this is the same in old machines, so that you can, if you are running small MPI jobs on Myriad and you suddenly realize you need to run a couple of hundred cores on Kathleen, you can take your scripts and data from one machine to the other and then run it seamlessly without much modification. And of course, it provides the same interface to users. As I've said, this is not just a software stack for traditional HPC users, right, which would be Fortran and C++. It supports Python, all varieties of Python, including Anaconda, PyPy, which is a JITted version of Python, R. We're very fond of Julia. There's Perl, there's BioPerl, Java, Clojure, Common Lisp, Scheme. You can run .NET applications through Mono, JavaScript, MATLAB, pretty much whatever you want to do. We have provided an environment you can do that in. We also have a lot of machine learning tools installed, so you can use the GPUs to do machine learning, and things like TensorFlow, Caffe, OpenCV are all installed. And if you have a departmental system administrator, we can give them permission to allow them to install applications for you as well. So I'm going to show you off how this is presented through a thing called environment modules. Right. If I'm in, let's just quick check on our job actually. Our job is run. So pinging back to the previous thing, if we look at our job, you'll see that there are now two output files here, one of which has got an E and the job number, and one of which has an O. The E shows any errors that happened when the job ran, but we don't really care about that because we're pretty sure that job ran fine. So let's have a look at the outputs in the O file. And there you can see that the date when it ran, and that it ran on node J00A-002. Right, modules. So, our system uses environment modules. This means that you can access all the applications through the module command. If you type module avail, it'll show you a massive long list of things that are installed. But what you're really interested in is changing something in your environment, right? So supposing we wanted to use Python. The default Python on Red Hat Linux, which we're using, is very old, but if we wanted to use Python 3.9, for example, we would do module load Python 3.9. I think this is the right way to do it. Yep. Do which Python. And it's picked up the newer one from Python 3.9. This is actually, the Python is actually deployed through what we call a bundle, which means there's actually a lot of pre-installed Python modules. So if you use Python, it's quite likely the package that you already want is installed. So things like NumPy are installed and SciPy and hundreds of tiny little things. But supposing that's not the right Python for us and we want to use Python 3.4, so let's say 3.7 instead, do module remove. One of the nice things about modules is if you mistype, so I accidentally typed list G rather than list T, it will autocorrect some of these things. You see Python is no longer loaded. And if we load Python 3.7, do which Python, see that it switched the path to Python 3.7. If we run it, the older version of Python, right? And that's true for a lot of our tools. A lot of our tools we have multiple versions of, particularly things like compilers, where either new features are added, but also new bugs are added at the same time. And that allows you to always run your job in the environment, same environment, right? You can say that you always want to run your job on Python 3.7 and not move to Python 3.9. Or you can move to Python, you can set it up so things are loaded automatically, right? It's kind of up to you. Okay. we have a common software stack. The code that builds and runs stuff, so all the applications, is in GitHub. So there's a URL there you can look at so you can see how we build those applications. We have a wrapper called GE Run that replaces MPI Run, and that's quite important because that interacts with Grid Engine that we wrote. That's also open source. We've put it on GitHub, but anyone can use it. One of the important things on the build scripts repository is, although these scripts will reliably build applications on our systems, they do rely on things that are unique to our machines. So you can look at them to get hints on how you might want to build something on someone else's cluster, but there are bits in there which will only work on UCL clusters. For example, it relies on this path shared UCL apps existing, and some include files that are inside that. One way you can ask for applications to be installed is to put in a ticket. You can also just open an issue on that repository and it should get picked up by the team. Right, so efficiency, right? This is not by no means going to be an exhaustive list, but here are some things to think about when you're running your code. Right, the most important one, I think, actually, is to be very pragmatic about this. Efficiency is important, but you live in the real world as opposed to the theoretical world. Lots of people who get interested in computational science are involved in where they care about the actual speed of the code. What you really want is, I've had an idea, I set off my experiment, I get the result as quickly as possible, right? So that means if you're comfortable writing code in Python and you've written the code, there's no point at all if you're just going to run it once learning C to rewrite it in C, right? It might be worth it if you're running it 10,000 times, right, or 1,000 times. You have to add up the cost of doing the optimization and compare it against the amount of time you save. Excessive optimization is madness, right? You can go down all kinds of rabbit holes when you're doing all kinds of things to the code, and then a compiler revision will happen and it will undo all of that work. It's completely worth slightly modifying your code to make it run 10 times as fast. And you will find things like loop ordering or fusing loops, which actually the compiler can generally do for you now, but in some languages those things will really improve the performance. So modifying your code to run faster. Most compiled programming languages, by default, when you compile a program, compile it in a very safe way. By safe, I mean it has very little optimization, because all optimization brings potentially unexpected behavior, and potentially performance decreases as well as increases because it's a compiler doing it. Also numerical accuracy problems. So there are things like in the Intel compiler, you can change the floating point model, which changes how accurate floating point math is. There's a really good Wikipedia article in there about how bad floating point math is, which is worth reading if you are excited by that kind of thing. You could rewrite it in a faster language, maybe. And it might just be that you're using the language wrong. A good example is it's very tempting as a traditional programmer to use loops in R, and that is horrendous from a performance perspective. So I'm going to show you a quick demo of how you can use compiler options to really speed up the performance of your code. So here we have a tiny program which estimates pi through a very bad numerical approximation. A quick look at the code. It's written in Fortran. It basically sums up the area under a curve, and that ends up being pi, right? We can compile that with a Fortran compiler. This might be a point where I should probably load a more modern compiler, but let's do it with the old one that's by default. Pi-f90-o pi default, we'll call it. And we compile it, and we have a binary, and if we run it, it'll print out some timing information, right? And we'll see how long it takes to run the unoptimized version of the code. It takes about 7.5 seconds. There's a very simple flag you can add in G-Fortran, which sets the optimization level up, and we'll set it to 2, because that's usually a good compromise. And if we compile that, oops, there we go, pi, we'll call it pi O2. And we run that, it should be faster. And indeed it is, right? It takes 1.9 seconds rather than 7.5 seconds to run the code. So that trivial little luck change where I just added a command line option in changed the amount of time it took to run. Some compilers, there's an option called fast, which produces really quick code that's really wrong. Okay, so there is a trade-off, but O2 is generally safe. File I/O. So computers are very fast, storage is comparatively very slow. Even on Myriad, which was very much designed to be optimized for I/O because because of the high throughput nature of it, it reads and writes a lot of data. It's still quicker to not do I/O if you don't have to. So think about how often you write out your data. And another tip that it's true of almost every HPC system, but particularly ones that use Lustre like ours, writing one big file is much quicker than many small files. And that's because the way the parallel file system works, every file requires access to a thing called the metadata server. So if you only have to do that once for a chunk of data, that's a lot less of an access than if you have to do it for several thousand of those. All the UCL systems allow you to request an amount of memory. That memory is per core, and it is enforced. So you cannot go over that limit that you set. If you exceed it, your program will start writing to swap, which is writing to disk, which is doing I/O, which is very slow. So when writing code, think about the memory efficiency. Our systems have between 4 to 5 gigabytes of RAM per core, 192 gigabytes of total per node, right? If you request more, the scheduler will underallocate the cores to compensate, i.e. 4 processes with 34 gigabytes per node. If you need a lot more, Myriad has nodes with 1.5 terabytes of RAM in total. Regardless of policy, right, almost all work can be broken down into many small tasks will run more efficiently than large tasks. So on Myriad, the optimum job size is about 1 to 2 hours in length for single core jobs. And the best way to do lots of work is to submit a thing called an array job. And what that does is you submit one job script, but it creates tens or hundreds of thousands, depending on what you tell it, copies of that job with different input data. On Kathleen, the most optimal way to get through the queue is 1 to 2 hours in 80 to 160 core jobs. The other thing to think about is small tasks are more recoverable. If a node crashes or there's a power failure, you'll lose less work, right? We often get people who ask us to give them access to extra long queues that are 2 or 3 weeks long, which we don't generally allow. But that is the reason we don't allow that is not because we're stingy, it's because the chance of you losing that much work is considerably higher than if you run smaller jobs, right? The system stays up as a whole for a long time, but individual servers crash. And if you need to run things for a long period of time, you should look into checkpointing and actually submit subsequent checkpoints as individual jobs. Parallelism will only get you so far. There's a thing called Armdale's Law. And what that says is that for everything that you do as a job, you can split it down into the things that can only be done in serial and things that can be done in parallel, right? And it shows the limit of scalability. So no matter how many cores you add, the bits that have to be serial will always take the same amount of time, and that's why you get scaling curves instead of scaling straight lines, right? It's generalizable to other optimizations, right? So they're talking about the writing files. The serial part is the metadata access. Reading and writing data is in parallel. And even when working on non-parallel code, like the limit to the overall speed up you can get by optimizing one part is limited by effectively the same law, right? Instead of being serial and parallel, it's serial and the optimized bit. One way around this is to use something called weak scaling. So strong scaling is making the same problem run faster as you scale it up. Weak scaling is you scale up the size of the problem as well as the number of cores, right? And this improves the parallelization because it increases the length of the parallel portion. So in summary of this whole thing, use SSH to access, treat keys as passwords, learn to make efficient use of the batch system, think about how and when you write out data, and if it's your own code you're running, think about what sensible improvements you can make, and be pragmatic. We have an email address, which if you send an email to, I'll go into the support board for my team, and someone from my team will look at it, and all the documentation for our services is on this URL.